Hello, and welcome to another episode of MAIN-iac Science Labs. I'm Mr. Andy, Youth Services Librarian for the St. Johns County Public Library System. And today we are going to talk about bridges, how they're built, what makes them strong enough to allow loads of people and cars and trains and other things to cross over them safely. Here we go. Look at that beautiful bridge. Building bridges for MAIN-iac Science Labs. Well, man has been building bridges for thousands of years. They can be as simple as a log bridge crossing over a stream. Just knock a tree down, cut some limbs off. There, you have a bridge. Pretty basic, huh? It can also get really complex, like this one, the Hong Kong-Zhuhai-Macau Bridge. It's 34 miles long. That is incredibly huge and incredibly long, and an amazing engineering feat to make that a viable bridge that isn't going to fall down. Wow, pretty cool. You can't even see the end of it. It goes way off into the distance. Now, whether it's a simple bridge, a complex bridge, it can even be kind of a weird bridge. There's all kinds of creative ways that man has invented bridges over the years. Check this one out. The living tree root bridge in Meghalaya in India. It's actually tree roots, living tree roots that have been woven together over many, many, many years, creating a strong, viable, and living bridge that helps people cross over these riverways in India. That's pretty cool. Well, man has been building bridges for thousands of years, and to put it simply, we've been working hard to improve travel for a long time. And we've experimented with some pretty ingenious engineering feats. Nowadays, there are four typical types of bridges: the beam, arch, truss, and suspension bridge. There we are, beam, arch, truss, and suspension bridges, or any combination of the above. There's even some newer, more experimental bridges that are coming around. They haven't gone into massive use yet. They're still working out the kinks on them. But they're getting very successful, very creative people. Bridges have to deal with stress loads in different ways. There's basically two major forces that are at play here. Those forces are compression and tension. Tension is the pulling force that can cause a bridge to pull apart and snap, thus bridge failure. There's also compression, which is a pressing force, which presses down on a bridge, which can cause it to collapse. And there's different ways to deal with these stress loads, and different types of bridges address these problems in a couple of different ways. Let's take a look at a few. This is your basic beam bridge. It's basically a horizontal beam with supports below it to hold it up in the air. About as simple a design as it gets. Well, not as simple as the tree log, but basically the same concept. Beam bridges are pretty limited in their ability to absorb compression and tension. Therefore, they can't make them very big. They can only go across small lengths of chasm or river before they become compromised. So what they've learned over the years is if you add trusses to a beam bridge, now you have a truss bridge, they become much, much stronger. These gridwork frames that can either go above the bridge or below the bridge dramatically improve the structural soundness of the bridge, and helping them deal with compression and tension in a much better way. The compression and the tension actually are forced through the framework of those trusses, spreading it out and dissipating the force, making it less of an issue and making the bridge considerably stronger. Now, the ancient style of bridges that you've seen a lot in ancient history and Rome and other places like that are these semicircular arch bridges. These were very popular for a long time because they were incredibly strong. They're also incredibly big, incredibly heavy, take a long time to build. But the semicircle structure of an arch bridge spreads the compression throughout its form and down into the support columns, and tensional force is distributed outwardly as well, making these bridges really, really strong, which is why so many of them are still standing thousands of years later. Tensional force is distributed outwardly, although they're still limited by their own massive structure. Take a long time to build, take a lot of materials to build. And if you build them too big, they're not strong enough to support themselves. So they also have limits to how large they can be and the size of an area that they can cover. So that brings us to the suspension bridge. Most modern bridges are now built in this style, especially if they have to cross a large canyon or a large body of water, because the towers of a suspension bridge absorb so much of the compression and the tension because of the guidelines and the cables and ropes that are running off from the towers to the bridge itself. The cables transfer compression from the bridge surface up to the enormous towers, where it's then transferred down to the earth where the towers are installed. And the cables also dissipate tension across the bridge. You see how they're spread so far? Really dissipates that force, making the bridges much, much stronger. Now, most modern bridges use a combination of these support types, not just one, as a way to manage compression and tension. Let's look at another one and see if you can spot the different types of bridges that are combined into this one bridge. Here we go. So you can see there's that grid work. That's the truss that goes along the beam. It also has the suspension ties and the towers to help spread it out. So that's an extremely strong bridge. Let's try another one, see if you can spot the different types in here. Oh, wow, look at this one. I don't see a truss in there, but they do have the arches and they have the towers with the suspension cables. So they've used a variety of techniques on this bridge and on this bridge to make them really super strong structures. Now that you know a little bit about bridges and how they work, let's try some experimentation. And we're not going to use concrete, we're not going to use steel, we're not going to use cables. We will use simple construction paper and a few other things. Here is the list of supplies that you're going to need. We need some construction paper, several sheets, because we're going to try a couple different experiments. You're going to need some tape. For some of your structures, you might need to add a little tape for extra support. Consider that you're welding. We're also going to need a couple stacks of books to be the edges of your riverbank or canyon. We're going to need a bunch of Legos, which you will use to test the strength of your bridge. Or, if you prefer, you can use a bunch of Matchbox cars to do the same thing. Now, Matchbox cars are a bit heavier, and they're on wheels, which makes them a little unwieldy. I prefer using Legos, but you can use really anything you like, as long as you can stack it onto your bridge and use some sort of way to measure how strong your bridge is. All right, so let's get out of the screen share and go right back to business. All right, let's do some experimenting. So I have my stacks of books here. I'll put them out. These are going to be the towers or the edges of the canyon that I'm trying to traverse. So the first sheet of paper we're going to try, and remember, you need to use a new sheet of paper for every different type of bridge that you use, because each time you make an adjustment to your paper, you're compromising its construction quality. So you definitely want to have a stack ready to go so you can start over as needed. So the first bridge we're going to consider is the beam bridge, a simple beam bridge, which is simply a beam, a horizontal beam, laying over top of your support system. So let's take this simple piece of paper, lay it on top of the support system, and see what happens. Instant collapse. What's the problem here? Well, obviously, our beam is not thick enough to support any weight, its own weight in particular, which is a major issue when designing a bridge. You have to make the bridge a certain weight. It has to be able to support its own weight. Think about, remember a few years ago when planking was a thing? When people would go out and plank their bodies on objects, where basically you held your body rigidly flat. Most people have a difficult time holding a plank for any period of time, 10 seconds, 30 seconds, 60 seconds. before their body starts to collapse because their bodies are not strong enough to maintain that rigidity. This sheet of paper is not strong enough to maintain its rigidity when there's a chasm below it, and it just falls right down. So what did they do with beam bridges to make them stronger? They made them thicker. So how can we make this sheet of paper thicker? Well, we can fold it over upon itself a couple times. Now, a sheet of paper, you can probably fold it in half easily. Let's try that. Let's fold it in half. Just measure up your corners, fold it in half, put it back on your chasm. Hey, it's holding. It hasn't collapsed on itself under its own weight, but can it hold additional weight? Let's find out. Take one Lego brick, set it on top. Hey, not too bad. The other bridge couldn't hold any weight. Let's see if we can get a second one on there. Not too bad, but it looks like it's starting to compress a little bit, doesn't it? Third Lego weight. Starting to have a little bounce to it, isn't it? Let's put a fourth one on and see what happens. Oh, complete disaster, complete collapse. So folding it over in half and doubling the thickness of that beam didn't work. So let's fold it over one more time, and that now has 4 folds, which gives it 4 times the strength, theoretically, definitely 4 times the thickness. Let's see how this handles the additional weight. Now, this is where tape would come in handy. Let's see if I have some lying around. I do. In my magical cabinet of things, I have some tape, because as you can see, our folded paper doesn't like to lay flat, which makes it hard to put weights on it. So I'm just going to put a little piece of tape. It's not actually creating any structural support. It's just making it lay flat. So we'll try that. All right, 4 times the thickness of our beam. Let's see. Did we get to 4 Legos last time? I think on the 4th Lego, we had complete bridge collapse. Let's see if this bridge, twice the thickness of the second bridge, will do any better. Let's try. Here's 1. So far, so good. 2. Oh, that's not so good. But remember at the beginning, I said you had to use a new sheet of paper every time because your structural integrity is going to be compromised. I think this is a case where we need to start with a fresh sheet of paper. Let's put that one aside into the recycle pile. So we're going to fold it in half, our new sheet of paper. We're going to fold it in half again, maintaining optimal structural integrity, and then a little piece of tape to make it stick together because it wants to flap open like that. Let's see if this does any better. Look, it's already bent in the middle. Maybe my taping is part of the problem. So that has 1, 2 Legos, 3 Legos, 4, and it still collapses in the middle. Apparently that's not enough. Should we try folding it one more time and see if it makes any difference? Got lots of paper. Let's give it a try. So we're going to fold it in half, fold it again, and then fold it one more time, making it 8 times the width, the thickness, making it theoretically 8 times as strong. And we'll see how if this makes any difference. Here we go. All right, new bridge. It's all bent up at the sides. Let's add a little more tape because it's being difficult. How many Legos can we get to hold up now? We've not made it past 4. We actually not made it past 3 yet. Let's see. 1, 2, and I'm dropping them very gently. We don't want extreme compression. 3. Here's the magic one, the 4th one. We haven't gotten this far yet before. 4 bricks. How many more do you think? Think we can make it to 5? Let's try. We made it to 5. Let's go for 6. Ooh, I'm feeling confident now. Can we make it to 10? Let's find out. 6, 7, 8, 9, 10. 11. Oh, we had collapse. Well, darn. Wait, we made it to 10. And then the 11th one knocked it down. Now, do you remember what they did to beam bridges to make them stronger? Added truss supports. So let's mimic a truss bridge for our next experiment. We're going to take a piece of paper and we're going to fold it. What's the best way to do this? Let's fold it about, to be about, and let me get a measuring device. My magical box of things, I have a ruler. So we're going to fold it about 1 3/4. And then go back, fold it again on itself backwards. And then again, like that. And then again, one more time. Basically, you're trying to fold it in an accordion style, so you get like a W. And this kind of mimics a truss bridge because instead of just straight lines, you've got zigzag lines that are helping to create support. So the super thick beam bridge held 10 bricks. The 11th one made it collapse. This is back to single layer thickness, but with the added zigzags. Do you think we can go past 10 bricks on this? Let's find out. Brick number 1, 2, 3, 4, 5. I am showing no flex whatsoever with 5 bricks. Let's keep going. 6, 7, 8, 9, and magic number 10. So far, this truss bridge is looking pretty good. How much further past 10 can we go? Let's find out. 11, 12, 13, 14, 15. Wow. Now keep in mind, this is single thickness, not quadruple thickness like the first one, like the regular beam bridge we did. Single thickness, but with the added folds, making that little bridge work, which is going to dissipate the weight, the tension and the compression. It's working really well. So we're up to 15. Let's keep going. 16, 17, 18, 19, 20. Do you think we can get to 25? Let's find out. 21. Ooh, we're starting to compress a little. 22. 23. Oh, I dropped that one. That was bad. 24. 25. Okay, the bridge is getting a little out of shape here, but it's still holding. So for safety, I wouldn't want this to hold any additional weight, but we are running experiments, so we got to get to the breaking point. So let's get to the actual breaking point. 26, 27, 28, 29, 30. It's definitely compromised, but it's holding 30 Legos without any issue. Let's keep going. 31, 32, 33, 34, 35, oh my, 36, 37, 38, 39, 40 Legos. I'm actually running out of Legos. 41, 42, 43, 44. I've actually run out of Legos. I don't think I have any more, do I? No, I've maxed out. So obviously the truss adds considerable strength to a regular beam bridge. Now this one it's all wonky, it's a little smooshy, but it's still holding. What else can we add to it? I don't have much else to put on it. How about my mouse? No, don't want to do that. Might turn off the recording. Oh, maybe it was just a matter of time and the bridge finally collapsed. You don't want to have to be that last brick crossing the bridge when it finally goes away. Now we know a truss bridge properly installed is a combination of the beam and truss. So let's try that. Let's make a combination beam and truss. Let's fold a sheet of paper into fourths, which will allow us to make a square. I guess the easiest way is to fold it in half. Open it back up, fold one edge to the middle line. And then fold the other edge to the middle line. So then you can shape it into a square. Now you're going to need to use a little bit of tape. This construction paper doesn't hold its shape all by itself. It needs a little assistance, a little coaxing, as it were. Structural integrity is important here, so try to make it as close to a square as possible with your taping. If it's a little wonky, your bridge is going to be a little wonky. Thankfully, you're not going to drive a truck across this. You're just going to stack some Legos on it. So it's just a scale size experiment, which illustrates a pretty powerful point about structural integrity in bridges. Okay, so now I've made a general square. It's a little wonky. Squished it, that probably wasn't so good. So then I'm going to take my truss that we built earlier. It's a little compromised, but not too badly. I'm going to fold it up accordion style, and I'm going to put it inside the square. And that's going to create our truss inside the bridge, which theoretically should make it pretty strong. So let's see if we can get all these Legos on top of it without having complete collapse. Now, previously when I tried this, my only issue was it folding over on itself. This is not a true truss where we don't have the beams actually affixed to the bridge. It's just kind of floating in there, but it's just to illustrate a point and showing its strength. You ever looked at a cardboard box on the side? You can see those waves inside it. That's the cardboard box truss system of paper to make it a very strong box. We're doing a similar thing here. So let's start adding Legos and see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we were pretty confident 10 would be fine, right? Question is, how farther can we go? 11, 12, 13, 14, 15, 16, it's a little wavy, 17, 18, 19, 20, 21, 22, 23, 24, 25. Starting to bend a little bit on the sides where I didn't tape it together. That's where good riveting comes in handy. 6, 7, 8, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. Oh, I thought I had 44 bricks. There's the last one. 44. Oh, see, now the bricks are falling off, not the bridge itself. Put them back up there. Getting a little structural integrity issue here. It's starting to bend in the middle, but we are able to get all 44 blocks up on top without the bridge itself collapsing. It's pretty awesome. Pretty powerful bridge. Could you get more weight on it? Potentially. What are some ways that you could do that? You could measure out a piece of paper to the height of the bottom of the bridge and build an additional support underneath there. Longer bridges require additional supports in the middle to help handle the compression of the weight pushing down. Pretty cool stuff, huh? I wish I had more Legos. We would see just how far this can go. Maybe you can see just how far yours can go. And if you can get more than 44 standard 8-pin Lego bricks on top of your bridge, I would love to hear about it, and I would really love to see some photos. See how big that Lego wall can be on top of your bridge. Go ahead and share it with us if you tried this experiment. We'd love to see it. Just go ahead and tag a picture in the comments section below the video. Pretty cool. We'd like to see what you can come up with your engineering skills at home for your own version of MAIN-iac Science Labs. Well, I'm Mr. Andy. Thank you for tuning in. I hope you learned something. Next time you cross a bridge, take a look at it. Try to figure out what style of bridge you're driving over or riding over or walking over. Is it a standard beam? Is it a truss bridge? Is it an arch bridge? Those are pretty cool. Or is it a suspension bridge or a combination of 2 or 3 or more? Things to think about as you look at the engineering structures all around you in your everyday world. Well, I'm Mr. Andy saying goodbye for St. Johns County Public Library System. I hope you enjoyed the program today. Hope you had some fun building with me, and I can't wait to see you again next time. Bye.